Okay, so we have spent a lot of lectures on DC analysis of the BJTs, and today we'll start with the AC analysis, and you will see. So just let me share the content. Yeah. Okay. So AC analysis we are starting with, and just like the DC analysis, in the DC analysis we had to make a DC equivalent circuit. In the DC equivalent circuit, what did we do? We opened the capacitances. So the capacitances were treated as if it was open circuit, and in the AC equivalent circuit we will do exactly the opposite. We will assume that the capacitances are chosen of such values so that the impedance to the capacitance is very low for the given AC frequency. Okay. So in that, with that assumption, we can ignore the effect of the capacitances and treat them as short circuit. So you see in the here you see, so this is the AC equivalent circuit, and what we have done, we have simply put a short in place of the capacitances. Wherever the capacitances are there, we have put a short. Okay. And now what we are doing, the difference is that we will now be dealing with the AC signal, the AC signal coming from the AC signal source Vs, and we are not dealing with the DC signal. So previously we were not dealing with the AC signal, only with the DC signal. Now we are not dealing with the DC signal, we are only dealing with the AC signal. So what we employ two things. First is the assumption on the different elements in the circuit, so capacitances are short circuited. Second is we utilize the superposition principle. Superposition principle says that if this is a linear system, of course this is a linear system, and I will not say it is a linear system, there is a nonlinearity here, but what it says here is that we utilize the superposition principle in this way, that there are two different sources which are impacting this system, and we have seen that this DC source does not get disturbed by this AC signal because of the presence of the capacitance. The DC does not flow back to the AC, and when we are dealing with the AC, that AC simply acts on top of the Q point that we have established in this circuit due to the DC. So when we look into the AC behavior, we can simply ignore the DC for the time being. We only keep in mind that there is of course a DC, there is a DC set point, that is a Q point, and the AC behavior is getting shown. The AC behavior is seen on at that Q point base level, at that Q point reference level. So at that levels of your IC, IB, IE, the AC signals are, the AC behavior is getting seen. So it does not get shown on top of a zero reference level. That is what we need to keep in mind. However, when we are doing the AC analysis, we are treating the DC level to be 0. You see here in this equivalent circuit, the DC source voltage is grounded. The DC source voltage is grounded. So we are treating as if there is no DC, and only the AC signal analysis we are doing. However, we have to keep this in mind. At the back of our mind, we must keep this, that the AC is acting on top of the DC reference levels that has been set in the circuit by the Q point, which we have already calculated. We have done a lot of analysis on that. Okay. So these 2 points we have to keep in mind while we are going ahead with making the AC equivalent circuit. Now this in this AC equivalent circuit we are seeing that there are several resistors now, a source, voltage source, and this transistor. So this is a particular configuration. There may be any number of configurations, and but the main thing is that we will see this, we'll encounter these things. We will encounter a voltage source, AC voltage source. We will encounter several resistances in the circuit and the transistor. Now from the point of view, so this AC equivalent circuit, we try to see it from the point of view of a two-port system. Now I guess that you have your previous courses have covered the idea of two-port systems. Can I have a response whether it is this concept has been introduced? Huh? Not introduced yet. Okay. Okay, so I will introduce it actually, then we can go ahead. And there is a course, I don't remember the name of the course, maybe network theory or maybe power systems also maybe. So in some courses it gets covered in more details. However, here we will be utilizing the concept of two-port theory. To understand what is the concept, you look at the AC equivalent circuit first, this circuit in the right hand side. Here what you are seeing, you note the variables which are written down in blue. Which are the variables? This II, Zi, Vi, I0, Z0, V0. Okay, so what are these? So this is the point where we are entering into the circuit. So you must clearly be able to demarcate several parts of the circuit. That is important. So let me show you one by one. This part is the source part. This part is the source part. It comes with the source along with the source resistance. Okay, so the source resistance is not part of the circuit as such. Whenever you connect a source to the circuit, a source resistance comes along with that source. It is not part of the basic configuration which we have made here. The basic configuration is this much only, and there is a load side. So from this configuration, from somewhere from this configuration in this particular diagram, from the collector point, we have taken out a terminal, and here we would be connecting a load. The load has not been connected yet, but if a load has to be connected, we would be connecting the load from here to ground. In this place it would be connected. So that load part is also not part of the circuit which we are utilizing. So this circuit can be treated as a system which has a output side where a load has to be connected and a input side where a source has to be connected. In this particular diagram we can see only the source getting connected, because unless you have a source connected, we will not be able to have any signals flowing through this circuit. However, connecting a source does not demand a load to be connected. We can keep a no load condition. This is called a no load condition. The circuit can be kept like a no load, with no load. So we have connected the source, but we are keeping the circuit in no load condition, and we are checking what is the flow of signals, what are the different levels of voltages and current in the circuit when it is in no load condition. Another condition gets established when we connect a load in the circuit. Then due to the load, there would be some alterations in the currents and voltage levels within the circuit. So that is the loaded condition of the circuit. So in any given circuit, you please identify the circuit is just a passive network without any voltage sources, voltage or current sources, simply a passive network. When we are connecting a source, only then it gets some signals are generated here, it gets activated, you can say. This source is activating the circuit, but this activation doesn't result into anything fruitful because we have not connected any load. Okay, fruitful means something we want to utilize from the circuit, and that utilization must happen at a load point, but we have not connected a load, so the circuit is simply active but it is not getting utilized by us. When we connect a load, then we are utilizing the circuit. So this is also a principle which you will find applicable in many different parts of your engineering study. Even in many different aspects of your life, you will find this principle to be applicable. Normally there is a system lying somewhere which is just lying simply. It doesn't have anything to do with anyone. Unless you activate that system, it is not able to get energized, so you can say. So once you activate it with some source, it gets some energy and then it can deliver some work. So it will be able to now deliver some work. In this system also the same principle is working. In the DC also, when we had not connected the AC, just simply look at the DC part. So when we are energizing with the VCC, only then it is able to do some work. Otherwise it is simply a passive network, arrangement of different resistance and capacitances and transistors, that's all. So this is a very beautiful principle. You will find this getting applied or getting manifested in many different areas of study in your life as well. So this is the thing. Now when we have understood this, so now we have been able to clearly identify that there is a system, there is a source side and there is a load side. When we have identified in this manner, then we can draw it or we can represent it as a two-port system. So you understand that there are two ports to this system. One is the input port side, another is the output port side. One is the input side, another is the output side, but we call them as ports for networks. So this is the input port side, as you can see in this figure. This is the input port side, this is the output port side. And looking from the input side, you will be able to distinguish. So in the input port, no voltage source is connected yet. In the output port also no load is connected yet. You look into this system, this only has the passive elements within this system, and these passive elements can be in any arrangement. So this is just a particular arrangement. This is a general system, general two-port system. So in these blocks there can be any arrangement of your passive elements. Looking here in this two-port system, general two-port system idea, in this configuration, whatever may be the configuration, how much may be the complexity, it will always be having some input current coming to it. When we would connect a source, obviously when we would connect a source here, there would be some input current flowing into the system, and at that input port some voltage would be established, Vi. Notice that this Vi is not the source voltage. Notice here in this diagram you will see it clearly. This Vi is not the source voltage, it is the voltage at the input port. Here the input port is formed by this terminal and the ground. This terminal and this terminal is grounded. This terminal is grounded. So Vi is the input voltage, is the voltage at the input port. II is the current coming into the input port. So this voltage, if it tries to deliver this current II, it would face some resistance from the system. Only think about this voltage and this current, the input voltage and the input current. This is the input voltage, input current, not the source voltage. There is some terminological difference, also conceptual difference. Please note this, source and input are not same in this case. Input we are calling as the input to this two-port system, the input port. A source voltage has to be connected to that input port to energize the system. Right now the system is not energized, but we are only considering that if at all there was some energy here, then there would be a voltage established at this input port, and this voltage would be delivering this input current into the system. While delivering this input current, it would be facing some impedance from the system. That impedance is called the input impedance. Previously in our discussions I commented on probably common collector, that it has a very high input impedance. So did not you are not very clear maybe what we mean by input impedance, output impedance. So now you will be more clear what we mean by input impedance and output impedance. So this is the input side. Similar concept is there in the output side. So when this is energized suppose this is delivering the output now. So when it is delivering the output, at the output port what we will see? We will see a voltage, obviously we will see a current also. So when we see this voltage and current at the output port, we can also ideate something called the output impedance, which is the impedance seen by the voltage while trying to deliver the output current. Then it would experience a impedance Z0. So you see, because we are trying to define an output impedance. Impedance is always defined in this way, that a voltage is trying to deliver a current and it is suffering some resistance from the system. So this voltage is trying to deliver this current. That's why the direction of the current is into the system. Although we know that normally the system will deliver the current in the opposite direction. That is the general case. Normally we will find that the system is the output current is coming out of the system. However, for the definition purpose of the two-port system, we have given the direction of the output current inwards. Only then the concept of Z0 stands. Only then the concept of Z0 stands. Okay. So then we can define a output impedance. Now while doing the calculations etc., you may find that I0 comes out to be negative. That would only mean that the direction of the current is opposite. The direction of the current is coming out of the system. Sometimes you may also find that I0 is positive. It might so happen. We don't know. So we don't know what is the actual configuration within the system. Everything will depend on that. So but irrespective of the actual actual circuit configuration, we can always define these variables at the input side and the output side. I hope this is clear. If there is any doubt, please ask me right away, because this is very fundamental now to proceed in the analysis of the AC analysis of the BJTs. Any doubt? Anything you want to ask? Okay, so you might also need some time to have this idea well established in your brain, but let us proceed, and while we are going ahead you will be more clear maybe. So just again reiterating what is happening now, the entire passive system which does not have the source nor does it have the load, that is now boxed in as a system now here, and the input side of that box we are defining the input voltage, input current and the input impedance. In the output side, output voltage, output current, output impedance. The directions of the current are always into the system. Both the currents direction are into the system. That's why we can define the impedance as positive. So we are trying to define the impedances as positive. That's why we have to make the currents go into the system if we established a polarity of Vi and V0 in this manner. So all these are in definition. In actual, you may find that V0 is negative. V0 negative means when Vi is having this polarity, V0 is having opposite polarity. That is the meaning of V0 coming out to be negative. I0 may come out to be positive or negative. If I0 comes out to be negative, it only means that the direction of current is in the opposite direction. Okay, but as per definition, our impedances will be positive, and you will also find that the in calculation impedances will come out to be positive if we maintain this sort of a definition. Okay, another important thing to note, we may sometimes make mistake here in our understanding as well as while we are trying to solve. This Vi is not the source voltage. Vi is only the voltage at the input port. There has to be a source voltage connected here, and when it gets connected, it comes along with a source resistance. At the output side, it is simply a resistance that will get connected, which is a load. Okay. So with this idea, with this, if we look here, we have simply simplified this equivalent circuit, AC equivalent circuit, to a more manageable form in this diagram. What we have done, we have noted down what are the common potentials. So these are the ground potentials which are common, and we have taken these at the same place. Achha, one thing I forgot to mention here, when we have done the AC equivalent circuit, this C had been shorted, P3 has been shorted, and since this is now shorting the RE, so the RE is not there anymore. Please keep this in mind. So whenever there is a capacitance which is in parallel to a resistance, the entire branch becomes shorted when you are doing the AC analysis. Okay, so this figure leads to this figure. So just pay attention that this R1 is now connected in this direction because it is with our ground, so it can be brought down here. This point, C point, from C point RC can be brought down to the ground at this side. So that is the thing that has been done. and R1 and R2 now sits in parallel. So this is a common resistance, which is R1 and R1 parallel R2. Now when this has been done, then this is Vi, the signal at between this point and this point. II is something which is flowing in here. Then you see the V0 is RC being considered as the load. So this is the V0 and this is the I0. I0 is flowing through the load. So normally we should draw the I0 like this. Okay, so it is coming from the load, it is not coming from this side because there is nothing this side. So the RC I0 has to come flowing through the RC load, and there is a impedance Z0 which is seen from this side. Similarly, there is a impedance Zi if it is seen from this side. Okay, and so if we compare with the two-port system, we can understand that the two-port, the system is only this much. The system here is only this much. This much is the system, and just at the input side of the system there is Vi and II. A source has been connected now and a load has been connected at the output end. So this makes a complete network. Complete network means the passive part of the passive system being connected with a source and a load. Okay. Now there are some points you just note down, that how we are doing the AC equivalent circuit. We are setting all the DC sources to 0, then replacing all capacitors by short circuit. Then if there is any elements being bypassed due to the capacitors getting short circuited, then they are also short circuited, and then we are redrawing the network in a more convenient and logical form as we have done in this picture. Okay, and this picture, such pictures can be made for any arrangement, and then we can start treating it as in terms of a general two-port system. Okay. Now we will check some configurations and try to ascertain what we are trying to ascertain. We are trying to ascertain Zi Z0. Zi Z0 we are trying to ascertain, and we are trying to ascertain what would be the V0 for a particular Vi. Or in other words, we are trying to ascertain the gain. Okay, in this initial examples the gain is not coming, but we would be coming into the gain very shortly. We would try to ascertain the gain of the network, the gain of the configuration. Gain meaning the output voltage is scaled by some amount with respect to the input voltage. The output to input voltage is the gain of the two-port system. V0 by Vi. V0 and Vi are the output and input of the two-port system. Okay, so that is the gain of the two-port system. So actually, if you see, what is the beauty of the two-port system, why we are going here and not doing very detailed analysis inside, is that if for some reason we can ascertain or we can know what is the Zi and Z0 and the gain of the system, then we don't need anything else, because when we give an input here, we can easily understand what would be the output by multiplying with the gain. If the gain is given to us, then we can understand what would be the output. And if the output voltage becomes known, we can always calculate what will be the I0 if the Z0 is known. Similarly, when if Vi is given, Vi is the input side, so should be given, and Zi is known, Zi is given from the two port systems parameter, so Ii can be known. So the different variables Vi, Ii, I0, V0 gets very easily known if we can know the Zi, Z0 along with the voltage gain of this network. So we don't need to know what exact configuration is inside the network. Whoever has built that configuration, if they supply us with the information of what is Zi and Z0 and what is the voltage gain, then we can simply treat it as a two port system and do our work. We don't have to analyze what happens within the system. We can treat it as a black box. But only thing is that the manufacturer or the supplier has to provide us with the Zi, Z0 and voltage gain. That they have to provide us. Okay. If that is not known, then we have to calculate it. And for the initial few configurations, we will calculate these parameters Zi, Z0 and the voltage gain. That is what your task will be. You will see in all these we will see some configurations where we will calculate the Zi, Z0 and the AV or gain. AV is the gain actually. So anyway, let us see one by one what we have here. So first, the common emitter. In the common emitter, we are calculating only the Zi in this case, just seeing at the Zi, trying to do some analysis. We are trying to do the analysis. Okay, sorry, I was skipping some steps here. Actually, first we have to also replace the transistor with a AC with a small signal AC equivalent circuit. That is what is shown here in this common emitter and common base, all this in these places. So that is what I was keeping in my mind. Sorry for that. So so let us again come back here. So if we have to calculate the Zi, Z0 and the gain whatever of the network, then you see within this network there is not just passive elements R1, R2 which are very familiar to us, but also a transistor sitting here. A transistor, how much impedance is it offering? So you see we have to calculate the impedance offered to the I0 current. So how we can calculate it? We can see the I0 flowing here and the V0 is here. What is the resistance here? We are not able to understand what is the resistance that is offered by the transistor. Similarly, here in the input side also we are not able to understand if there is some resistance offered by the transistor. So because the transistor is not simply a resistor, it is a new element, it is a new device which has a lot of things going on inside it. So to ascertain the two-port parameters, we have to, or to not just to ascertain the two-port parameters, just to even to solve the circuit in any manner, we have to first formulate what is called the small signal AC equivalent circuit of the transistor. Small signal AC equivalent of the transistor we have to formulate, and there are two types of such equivalent transistor models. These are called the transistor models actually, small signal transistor models. So the first model is the RE equivalent model, is called RE equivalent model, and another is called the hybrid equivalent model. Now we first take up the RE equivalent model. So here we are seeing the RE equivalent model of the common emitter configuration. So the transistor here is in common emitter. So if the transistor is connected as a common emitter, then what would be the RE equivalent model of the transistor? You see here, when you look into this configuration, is the common emitter. The emitter is connected to the ground. Base current is flowing here in this base terminal. A collector current of course is flowing, that's giving rise to the emitter current. But now we have to understand what is happening in this part of the circuit and in this part of the circuit. So this is the input circuit. There is a diode here. In the input circuit, this BE, between these points BE, there is a diode. This we know. There is a diode which is forward biased. So this part we can replace by a diode. Only this part between B and E we can place a diode. So this point is the B point. This point is the E point. Between B and E we place a diode, and the current IE is flowing through the diode. What is between C and E? Between C and E, the current IC is flowing. In this part, the current IC is flowing. Between C and B, current IC is flowing. But that current is beta times the current IB. So we can treat it as a dependent current source. You have been introduced to dependent current sources and voltage sources, I believe. But even if you have not been introduced, so this is depending on the current IB, so we can treat it as a dependent current source. It is a current source because we know the current here is fixed. It is fixed by IB. We are very sure about the current here, not sure about anything else, but we are sure about the current which is flowing in this branch. That current has to be beta times IB from the transistor behavior. This is the inherent transistor behavior. It multiplies the base current with beta times, 2 beta times. Okay. So what we have done, we have replaced this transistor with a diode and a current source, like this. With the base point in between the current source and the diode, the base point is taken out, and the IB is flowing here, IC is flowing here, IE is flowing here. Another just notational thing you please note, that now we are writing in small alphabets. So this IB, so the subscripts are in small. Previously in DC the subscripts were in caps. Now the subscripts are in small. This is just a notational thing, just to indicate that we are now treating the AC signals. AC signals are treated with small letters. Okay, so this being the Bjt equivalent circuit, so this is the this can be treated as a equivalent model of the same Bjt. This is taken further, one step further here in this circuit, where we understand that when the current is flowing through the diode, there is a small resistance the diode is offering to the current. That resistance is called the RE resistance. RE, because it is in emitter. E means emitter. This is the RE resistance. What is the RE resistance? By the theory of diode, if you go back to the diode, you will see that there are 3 types of resistances: DC resistance, AC resistance, AC average resistance. So there this resistance Re, which is the resistance it is offering to the, I think this is the average AC resistance, I don't remember very well, that was equal to this thing. By formula it was equal to 26 millivolt divided by capital IE. Capital IE means the DC current, DCIE current that is flowing through it. This is getting established by the Q point. IE is nothing but IC. The Q point current 26 millivolt divided by that current gives you the dire resistance. Okay. So this is Re. Note one thing here only, that this is the only place in the entire AC analysis where we will see a DC parameter coming in. After this point, there is nowhere else in the AC analysis that the DC analysis interferes. This is the only place where the DC analysis sets some Re. The DC Q point will be able to set some Re resistance. That is the only thing it does. Due to the establishment of the Q point, this Re resistance gets established in the AC equivalent circuit. You can understand, the higher the Q point, lower this resistance. Okay. So talking about that, next what we can do, next we can have this figure represented in this manner, in the manner of a two-port system. Again a two-port is coming, but this two-port is now just the transistor, not the entire circuit, but simply the transistor. So here you can see how we are treating it. This is the input side, VBE, IB, input of the transistor. What is the output? The output is IC, and this much here the this IC is flowing. You can see this IC is flowing. Okay. So now if we look from this side, what is the ZI? What is the input impedance that this IB experiences? You try to remember, in the common emitter configuration, the emitter resistance is reflected in the input side by beta plus 1, scaled up by beta plus 1. This was very important. I also told you that time. This is very important. So this Re resistance is reflected in the input side as beta plus 1 Re. Okay, why? This is also very easy to note. Here again I have shown this, that VBE, the VBE is nothing but IE Re. So IE is nothing but beta plus 1 times IB. So it is as if that if you have VBE by IB, you will get beta plus 1 Re. So it seems that ZI is nothing but Re reflected to the input side and scaled up by beta plus 1. Now we can make an approximation and write it as beta Re only. So it is written as beta Re only. So from the input side, what we are seeing a voltage, and which is trying to deliver a current, which is suffering a which is facing a resistance. What is the resistance? If there is a voltage here VBE, a current through it, the resistance we know beta Re. So this resistance will be beta Re. That's all. In the output side, what we need to know? We need to know the current, the output current. The output current is simply beta IB. So we have written down this beta IB source dependent source in this side like this. So the current IC is equal to beta IB. So from this arrangement of elements, whatever information we have obtained by the equations, we are trying to represent it in a circuit form. That circuit, which is nothing but the representation of the different equations we are getting from analysis of these equivalent circuits. So this circuit can be treated now as a model of the transistor, So instead of drawing the transistor, which does not reveal any resistances or any information about what it is doing, we replace it with this model, AC equivalent model, and there the resistances and its behavior, everything gets very clear, and we are able to work with it simply in terms of circuit analysis that we are very used to do. Now one thing is that we also told that whenever we are treating anything as a two-port system, we must have an input impedance as well as an output impedance. But we have found out what is the output current, but we have not found out what is the output impedance. So normally this output impedance is very high, but even then there is some output impedance. What is the output impedance? VCE divided by IC. So the change, there is AC also, so there is some change in VCE that is producing some change in IC. So delta V by delta I at the output side would be the output resistance RO. So RO can be defined in this manner, and this RO is now shown here in parallel to this. Why in parallel? You may ask the question, why in parallel? Note that the current is flowing in this place IC. This current cannot come in this branch. There is no current in this branch because there is nothing that is connecting these 2 points. These 2 points are open. So the current is flowing in this branch. Like this, the current is flowing. Now the voltage has appeared here. The voltage has appeared here. So the resistance, of course, would be V0 by IC, and that resistance is now in parallel, has to be in parallel. Okay. So that is why this resistance is connected in parallel. Now what is the value of the R0? That is the question now. So there is a concept called early voltage, and early voltage is nothing but you have seen the collector characteristics. The collector characteristics are often drawn very flat, but they are not exactly flat, they have a slope like this. Now it was interesting to observe, and someone named Early who observed this, that's why it is called early voltage. He observed that all these slopes can be extended and they come and join at the same point on the horizontal axis. This point is called the early voltage, VA. What is the significance of this? The significance of this comes when you are trying to calculate the output impedance RO. Output impedance is nothing but the voltage by the current. So delta V by delta I. Now you see this is a slope, that would be the slope of this curve, that is R0. The slope of this curve can be easily obtained by simply dividing this perpendicular height by this horizontal distance, be it in any of this curve, you simply take the Q point. This is a Q point. You simply take the Q point, you note what is the IC and you note what is the VCE. VCE will be this much only, but since this is the early voltage which is common to everyone, so you can simply add this VA to the VCE. Add this VA to the VCE and then divide by IC. Now another interesting approximation has been done, which is that since VCE is very less than VA, VCE would be very less than VA, so we can approximate the numerator as VA only. So no matter what is the Q point, the R0 simply depends on the IC, output current, that's all. VA is constant. This is an approximation of course, but quite a valid approximation and it works. The R0 is very high in any case, becomes very high. VA is also very high. This is not to scale, this may be very high actually. So VA is very high. IC also is quite less, so R0 would be very high. IC is less means it is in milliamperes, right? So R0 is quite high. So now we have a complete RE model of the common emitter configuration. Complete RE model is now obtained and it looks like this. So please remember this model, like put it in memory, and it is not hard to remember also. The input resistance is simply this beta RE, and in the output side there is this current source beta IB which is pointing downwards, and an R0 in parallel to it. R0 has to be calculated, RE has to be calculated. This R0 and RE are the resistances coming into the equivalent model, and they are the ones which is who are getting decided by the DC bias. Here also you can see this is also from the DC Q point. The DC Q point is deciding the resistances. And this RE and R0 will have some influence on the AC behavior. Now the common base, this is a common base where the base is common now. Base is a common potential, and now this place input side is the EB, VEB. Now this is the input is IE and output is IC. But when you treat it as a two-port system, you have to talk about II and I0, Zi and Z0. Now there is this resistance RE in this side, in the emitter side, but the input is also from the emitter side. So the resistance is not getting reflected by any amount, it is simply RE. So we are simply writing down RE here. In the output side, this I0, the current IC is getting delivered, which is alpha times IE. We know that alpha times IE current is in this direction, and the resistance R0 has to be placed here, which is the resistance seen from this side. Now for the common base configuration, the output characteristics is very much flat. For the common emitter configuration, the output characteristics were having some slope, but the common base characteristics, although we normally treat them as the same, but to be more precise, the common base characteristics are flatter than the common emitter characteristics. And now you can understand that the R0 would be very high, almost infinite. in mega ohms it is. So, in many cases you will find that this R0 is not even placed in the equivalent model because it is so high and it is in parallel. That is why you can treat it as an open circuit. REO is obviously 26 millivolt IE. Just 2 points I will make before I conclude today's class. There is also common collector configuration, but in common collector configuration is almost like common emitter configuration, because the base will be the input, so it will see the emitter resistance. If there are collector resistance, along with the collector resistance it will see them reflected to the input side with beta times, and the output will be the collector current, which is beta IB. So it is the same equivalent model. The equivalent model is same, so we are not showing it differently. The equivalent model is same. So and the next thing is that, what about PNP and NPN? Will there be any difference? There will be no difference, because we are dealing with AC signal. So there will be sometimes it will be having a positive polarity and it will be having a negative polarity, but it will behave in the same manner. So we are seeing the AC behavior, we are not talking about the DC behavior where the polarities are fixed. So the NPN and PNP behavior will be the same. So the AC equivalent model will also remain the same. AC equivalent models will also remain the same for PNP and NPN. So with these points I conclude now. So today you have learned what is the AC equivalent circuit, the total equivalent circuit, what approximations you have to make, and you have learnt about the RE equivalent model of the transistor. The RE equivalent model of the transistor. With these ideas we will proceed to solve several configurations and find out what are the different variables with different elements in those configurations. So okay, I stop the lecture now. So if there are any questions or doubts, please write me, and in the next class I will present them and I will solve them. Okay, thank you.